Good morning, good day, everyone. My name is Tony. I am a course advisor at EIT. I will be your host for today's webinar. Before we begin, I would like to cover some few notes so that everyone get the most of the session. So on your screen now, these are the notification and sounds. So you are able to switch on and off your notification and sound as you wish during this webinar. And please post any questions under the Q&A functions at the top right-hand corner. If the question it has to do with today's topic, our presenter for the day will be able to answer those. But if it has to do with our course offering at EIT and ECT, I will be able to assist regarding those. Okay, so these are our frequently asked questions. So everyone registered for this webinar will receive a copy of the PDF slide and a link to the video within the next 2 business days via an email. So please do check your junk folder, spam folder, if it does not appear in your inbox. And we also provide a free digital certificate of attendance for live attendees. So we will then be giving a link and a QR code to a short survey provided at the end of the session. So please do stay with us until the end of the session to qualify for the certificate of attendance. Just a bit about Engineering College of Technology, ECT, and the Engineering Institute of Technology. Both of the institution focuses exclusively on engineering and technology, offering specialized courses for high demand industries. We have professional certificates, which are our short programs, to our highest qualification, which is Doctor of Engineering. Both institutions courses are built by global experts and delivered by experienced engineers, ensuring practicals, job readiness skills that are valued by employers. So ECT offers UK recognized qualification, whilst on the other side, EIT provides Australian accreditation qualification, many of which are recognized under the Global Engineering Accords. So basically then both institutions also offer a range of professional development, as I've mentioned, the 3 months programs. We offer a personalized student support. Those are the learning support officer. They do assist students throughout their programs with us. And also EIT and ECT respectively have a global learning community with students and members of faculty based across the globe. International networking and opportunity broad is then enhanced. We also offer a world-class education at an affordable price through innovative delivery and business model. I will be sharing a link to those at the end of the webinar. Moving forward, a disclaimer: the courses and qualification mentioned in this presentation are offered by separate legal entities operating in different jurisdictions. One in Australia and one in the United Kingdom. Each entity is subject to its own local regulatory requirement and accreditation standard. Prospective students should refer to the relevant institution's official website for accurate, up-to-date information specific to their location, including course availability, fees, regulatory status, and enrollment conditions. Below, those are some of the links, and I will also be sharing them with you. Moving forward, so EIT and ECT, we offer a group training for companies. We aim at empowering technicians and engineers with practical industry relevant skills. And for this particular product or services, you can learn more and contact our product manager, Cameron Gill. the email, or his email rather, is on the screen. So we offer a variety, as you can see. We have customized content tailored to your business need, hands-on practice with remote engineering labs, pre-start consultation and instructor matching, and we also offer continuous support via learning management portal. So you can take our product manager's details if you are interested in such. So some of the reasons why students choose EIT, as you can see, number one, Australian provider for students' overall satisfaction in postgraduate engineering programs. We came also top three in Australian provider for quality of education experience for undergraduate engineering programs. Top three also in Australian provider for student support for postgraduate engineering programs. So on screen, so these are some of the awards that we were able to win. Actually, that was in 2024, last year. We won the 2024 Australian Export Award for International Education and Training. We also won the 2024 West Australian Export Award for International Education and Training. Okay. Today's topic will be the recent advancement in semiconductor switches, and our presenter for the day will be Dr. Hamid Amin, who is also an EIT lecturer. Mr. Dr. Hamid, you can, I think, take over and share your screen.
All right. Thanks, Tony, and hello, everybody. Can you hear me okay? I'm just sharing my screen. Can you see my screen?
Yes, I can see my screen. I can see your screen. Yes, let me just ask the attendees, but I think you can carry on, sir.
All right. Thank you very much. Thanks to me again, and welcome everybody to this session. Today we are going to talk about the advancements in power semiconductor devices. So power semiconductor devices, they are everywhere in our modern way of living, from your phone charger, from your laptop power supply, electric vehicle chargers, renewable energy that's integrated in our everyday life. If you're old enough, like myself, you probably remember when the phone chargers used to be bulky and heavy, and they used to get, hot very easily. Now, compare it with chargers now, they are small, they are lightweight, and they are more efficient. And this is just one example of advancements we have made in semiconductor switches. So power electronics underpin modern electrification. The same transformation happened to the phone charger is now happening to transportation with electric cars, with electric train, to data centers. We understand how important data centers are now these days with advancements in AI and in power grid. The other thing is we are aiming to achieve net zero by 2050. Achieving this goal is not possible if we don't have high, very efficient, compact, and reliable converters. And the engine behind converters are semiconductor switches. Now, to give you a background, switches, semiconductor switches were based on silicon. that is the mature technology that's that was used to make transistors. And transistors, power switches, they were used the same technology of silicon, but silicon now faces some issues with the efficiency, with switching speed, with temperature limitations, and silicon is not anymore suitable for next generation of application in power grid, in solid state transformers, in high frequency applications. Now we have wide bandgap switches, not only transistor switches, diodes as well. So when we talk about wide bandgap devices, we are really talking about silicon carbide and gallium nitride. Now, wide bandgap. So these are you see on the screen, these are the benefits that wide bandgap devices they offer, right? They have wider bandgap, so they have higher voltage and temperature tolerance. So if you don't know what bandgap is, so you have your conduction band and you have your valence band. So in your valence band, all of your electrons in your atom, they are bound to your atom, right, to the crystal. So they cannot move, they cannot contribute to the conduction of the current. Now, you have to move these electrons from the valence band to the conduction band, where electrons are free, like metal, right? The electrons can contribute to the current. Now, the difference between conduction band and valence band is called energy gap. That determines how much energy you need to excite an electron to be bound to the crystal, all the way to conduction band, to be part of the current conduction. In the next slide, I will explain this a little bit more, but this property, exactly having a wide bandgap, leads to being able to tolerate higher voltage and higher temperature usually, and also it offers higher switching speed. Okay. Generally speaking, when we talk about power electronics, we are talking about a switching action, turning on and off a switch, right? Can be transistor, can be a diode, okay? Generally speaking, if you have a higher switching speed, the less or smaller passive components, like your transformers or your capacitors, this kind of thing, you need a smaller. So that explains why the devices we have now, they are becoming smaller. Like the charger, I gave the example. Before they were big, now they are small because we are using wide bandgap transistors. Therefore, we can use a smaller passive components in them. So generally speaking, the size of power switches or power devices, power electronics, they become smaller. Another benefit that wide bandgap switches offer is low on resistance. So this low on resistance will lead to lower conduction losses, which increases the efficiency, right? We always want to have higher efficiency. Now, wide bandgap devices, silicon carbide based, gallium nitride based, they are already available. They are commercially available. You can buy them, you can use them in your circuit. But we always try to push the boundaries, right? Find the next material. Next material, we call them, in this field, we call them ultra wide bandgap. As you can imagine, the bandgap is even bigger than wide bandgap devices. Material which fall in this category, they are diamond, they are gallium oxide, aluminum nitride. These are currently at research stage. They are not commercially available, but that's part of the advancement in semiconductor switches. Now, let's talk about material a little bit, because that seems to separate us from, silicon, wide bandgap, and ultra wide bandgap. So silicon is your, traditional material to use in switches. It's a very mature technology. We know how to, use silicon to fabricate our switches. We push the boundaries to go very, very small, for very small devices. We completely understand how to deal with silicon devices. Band gap is 1.1 electron electron volt. As you expect, wide band gap, they have higher band gap. Silicon carbide has 3.5, GaN has 3.4, ultra wide band gap, it has even higher, 5.5, 4.8. Now, the next category, that's band gap, the difference between conduction band and the valence band. The next property that's very important when we talk about a material that is used for transistor is called breakdown field. So basically, breakdown field is the maximum electric field that a material can withstand before undergoing avalanche breakdown, right? So you can imagine electrons can move, all right? Because they are moving at very high speed. They could move at very high speed. They can hit the next atom and then they release the electron, right? And those two, they release another two, that becomes like an avalanche. And that's a breakdown. That's that can be destructive process. That's why the breakdown field is very important, because we know the limits that a device can operate at. The unit for that is usually is a megavolt per centimeter. All right. So the wider the band gap is, the higher breakdown field it will have, right? Silicon is 1.1, that translates to 0.3. As you can see, this 3.2, that translates to higher breakdown field. GaN, even higher, right? Diamond 10, which is, the highest we can get from ultra wide bandgap transistors or switches. The other property that is also important is thermal conductivity. So thermal conductivity is important because we run these switches at very high voltage and high current, okay? And because power is dissipated in them, they usually end up having very high temperature, okay? The easier you can conduct this heat away from the device, the better, right? That's why you have heat sink and this kind of thing to dissipate. So even for silicon carbide and GaN, this value is very high. So that's for high power application, which is the topic of today, is it's desirable to have a high value for this. The things that you notice here is although the gallium oxide offer a very good band gap, 4.8, very good breakdown field, which is 8. The thermal conductivity is very low, which is kind of bottleneck for using gallium oxide in power applications. Okay, like I said, these two materials, they are at the stage of research still. So we are not having a commercial device until we solve the issue with this thermal conductivity. There are ways to go around this. The packaging of the components plays a big role, how to dissipate the generated heat, but is it active research area for diamond and gallium oxide. Now, we have this, I've introduced to you 5 different materials. There should be a way for us to compare the theoretical values or theoretical benefit of each of these devices, each of these material in power application. All right, that is called Boliga figure of merit, or BFOM. Okay, it's a fundamental metric in power semiconductor devices. It is designed to evaluate and compare the theoretical performance of the material. Okay, so the higher this BFOM is, material is more superior, has more potential to achieve lower specific on resistance at higher voltages. Okay, so at the end of the day, the higher this BFOM is, it's more, you can make a more efficient and compact power switch. Okay, so as you can see here, silicon sits here. That means for breakdown of 100, the specific on resistance is around 10 ohms centimeter squared. Compare that with diamond, which, you know, at 10,000 volts has less specific on resistance. Okay, 10,000, almost 10,000 volt. You know, half of that is specific on resistance. So a specific on resistance is very important, obviously, because that directly relates to the amount of power you dissipate or you waste. Okay, ideally you want to have a smaller and a smaller and a smaller specific on resistance, because you don't want to dissipate any power. You want to use all the power that you generate, right? You don't want to waste anything. So that shows diamond is a very good candidate for power applications. And this is 4H silicon carbide. This is GaN. These are, you know, devices that already have commercial devices. You can buy them. This is where your gallium oxide is, aluminum nitride as well. Yeah, so this is the way you can compare. Now, very brief overview of these two commercially available devices. Silicon carbide based devices, that means transistors, MOSFETs mainly, and diodes. They are commercial since around 2001. Okay, the major suppliers, they are Cree, they are ROHM, they are Infineon, ST Microelectronics. These are the main suppliers in the world. Cree is based in US, Infineon Europe, and ROHM in Japan, if I'm not mistaken. Now, these devices, they are available up to 2 kilovolts. You can purchase these devices. Prototypes, they are around 15K. I'm talking about discrete devices. I'm not talking about modules. Modules, you know, the voltage is higher even. So for discrete devices around 2K, you can commercially buy. I have seen 3.3 as well, but you know, they have some hybrid in them, so that's why I didn't add them in this list. But prototypes to 15K, expected scalability is 30 kilowatt. Now, key challenges, crystallographic defect is one of them. Oxide reliability is one of them. So oxide, to explain what oxide reliability is for silicon carbide is MOSFET, for example. Take MOSFET as an example. For MOSFET, you need to have a layer of insulator, okay? Between your silicon carbide, you need to have a layer of insulator. That insulator is usually SiO2, okay? Now, the easiest way in silicon, because you have silicon to make SiO2, literally you have to burn or put it in, burn is the simplest term to use, but you put them in a furnace at high temperature, you introduce oxygen into the system, and you make SiO2 at the interface, right? And then that can be used for gate insulator for your MOSFET. Silicon carbide, you know, you have Si in it, so you can still introduce the same process theoretically, right? So you can have silicon carbide, introduce oxygen in the furnace at very high temperature, oxide interact with silicon part of silicon carbide, and then you can create that SiO2 that you need, right? But the problem is here now, you have that carbon that is left in the interface, or a lot of other issues as well. But that introduces a lot of imperfection into your system. Now, that causes reliability issues, right? When you want to, have these devices made, you want them to be reliable. If you apply a voltage at the gate, you want the device to be turned on and off, not, sometimes on, sometimes off, sometimes at, difference on resistance. So this issue still exists for silicon carbide devices, the reliability issue, but we have managed to reduce this problem to very big extent. So it's still a active research area, but oxide reliability, we are having a grasp, we are taking control over that. EMI, electromagnetic interference, is another issue. I will discuss that in the next slide. This is for both silicon carbide and gallium nitride. Now, the other material, gallium nitride, the issues with that is uses foreign substrate. You can use silicon carbide, sapphire. So to give you a better understanding of this, when they let's start with silicon. With silicon, you can have slices of silicon crystal, right? And then you build your material on it, okay? But for GaN, there is no pure GaN slice, right? Like you have in silicon. You have heterostructure wafers or heteroepitaxial structures for that. So you need to have your substrate. You can look at substrate as your foundation, right? Substrate is your foundation. You can put the next layers on top of that. So you start with a foreign substrate. That's foreign substrate, like I said, can be silicon, that can be silicon carbide. The problem with that is because there are a lot of mismatch between silicon carbide, or sapphire and your GaN. It translates all the way to the top layer, okay? Because it's like putting bricks on top of each other, right? If you don't put them perfectly on top of each other, the higher you go, you can imagine this is more tilted. You can imagine that. And that will cause an issue for us later on. Okay, so this is one of the issues with GaN currently. But we have managed to make commercial GaN HEMTs. This is one type of transistor, high electron mobility transistor. We are not going to go into that today, but they managed to make around 200 to 650 volt commercial GaN devices. And this GaN is better at higher frequency applications. Still issues with current collapse. Current collapse basically means your current, drain current is usually drops, okay? Especially after a high voltage switching application, right? Which is, undesirable thing to happen. You don't want your drain current to drop. So it still is a problem. The substrate mismatch, I explained that because of that foreign substrate. And another issue is CMOS integration. At this stage, you cannot integrate your gallium nitride in your CMOS. Okay. Now, very brief silicon versus gallium nitride, silicon carbide. Silicon carbide dominates high frequency, high power, high voltage application. GaN excels in low voltage and high frequency application. This is just a very brief, very quick overview of ultra wideband gap devices. Keep in mind all three of them, they are still active research material. There is no commercially available device out of this material, but aluminum nitride is, the issue is chemically stable, but thermally limited. That's the issue. Gallium oxide has a good high band gap, is a is very inexpensive, which is a good thing when you want to produce in your mass production. But the problem is, as we saw, it has low thermal conductivity. Now, diamond has exceptional performance, but commercialization faces major hurdle in fabrication and doping. Some fabrication issue with that is not commercially available still. Really quickly talking about, I'm cautious all the time as well. Really quickly talking about technical challenges when it comes to wide bandgap and ultra wide bandgap devices or switches. Material defect is one of the issues. I already talked about GaN, the mismatch that will cause some reliability issues for GaN, and also the SiO2 interface for silicon carbide. Still, you have defects somewhere in your device that affects the performance. Therefore, it affects your reliability. Also, it affects your yield as well. Okay, so this is one of the issues, technical challenges for wide bandgap and ultra wide bandgap devices. The fabrication, when it comes to fabrication, like I said, silicon is very mature technology. We can fabricate silicon devices. We have the equipment for it. We have the processes for that. That is different for silicon carbide and GaN devices. They need unique processes, okay, and unique machinery as well. I have mentioned a few names here. The name themselves, they are not important because we are not going into what they do. Just wanted to mention they have unique processes for that. So still is maturing, but still we have some issues that trades off the scalability, quality, and cost. Okay, we are talking about producing something, in mass production. Obviously, we have to be aware of the scalability, quality, and in cost. It's not about the device itself. It's about, can we make millions of them per year or not? So that's still an issue. Thermal management is another issue. We briefly talked about that. The wide bandgap and ultra wide bandgap material, they have very high thermal conductivity compared to traditional silicon, which is a good start. But still, because we are pushing the bar so high, meaning the power application we are using is just simply too high. The power is too big, so it naturally produces a lot of heat. So thermal management becomes very important. One way to go around this is advanced packaging. The way they package the device after they fabricate the device, the way they package the devices plays a very vital role. How that device dissipates power or heat. So that's another area that needs attention when it comes to wide bandgap and ultra wide bandgap devices. The next issue I wanted to mention is parasitic and EMI. EMI, I discussed it before, is your electromagnetic interference. Okay. So these switches, they are designed to operate at very high frequency, on and off, on and off, on and off. That's how they are designed. Power electronics is based on that. Now, if you very quickly switch a very high voltage, basically that high dV over dt, meaning the rate of change of voltage with respect to change of your time is very big, which is expected for wide bandgap transistors or wide bandgap devices. That introduces some transient in your currents and voltage, right? And that transient current and voltage will introduce EMI, electromagnetic interference, which has to be taken care of. Ironically, so just to give you an example, the reason for this is because one of the reasons silicon carbide and GaN devices are desirable is because they operate at high frequency, right? So high frequency is a good thing, but at the same time, if it operates at a very high frequency, it causes some issue. So the benefit becomes its own enemy, right? Because now the parasitics are very small, because if the parasitics are very big, that transient that I'm talking about, that can dissipate, right? Higher capacitance can dissipate. But the problem is with wide bandgap or ultra wide bandgap devices, that transient, because the transient is because the parasitic capacitances are small, that transient cannot dissipate easily. Okay, like I said, you can look at it as in benefit becomes enemy of the device itself, or the enemy when you are using it in application. Therefore, you are using snubbers for that. The snubbers are designed to dissipate that transient that is generated. Long-term reliability, I briefly spoke about that, is another technical challenge when it comes to wide bandgap and ultra wide bandgap devices. If you operate this device at very high voltage at very fast, it's not reliable. Simply is not as reliable as silicon, for example, devices are. So these are still active research areas. Now, I talked about the to recap what we have discussed, I talked about the wide bandgap devices, ultra wide bandgap. We talked about the how they show superiority compared to other material. We talked about some technical challenges, but now let's talk a little bit about application of this wide bandgap devices. I have a few of these, but it's not limited to the list I have. So first one is solid state transformers. We know what a transformer is, right? Low frequency transformers. They are bulky. They can operate at the line frequency. We are talking about the line frequency, which is 50 to 60 hertz. Okay. Now, the cross section of that transformer, the core, is inversely proportional to frequency. Meaning, if I increase the frequency, the core cross section becomes important, which is something we like. Because we would like to make a small device, smaller devices, right? So SST is solid state transformer, meaning that basically we want to replace low frequency transformer with a modular converter based architecture using medium frequency transformer. Remember, low frequency has bigger core cross section. If I increase the frequency, I can shrink the size of the transformer. That's the goal. The basic idea is to replace the low frequency transformer with a power electronic converter plus a much smaller transformer, which can operate at higher frequency. Instead of 50 hertz, they can operate in kilohertz or tens of kilohertz. Also, this SST, based on wide bandgap transistors, can be used as as a vehicle to make bidirectional power flow, right? Because we would like to integrate our devices, our systems to renewable energy, right? To give you an example, during the daytime, okay, you can charge your car, electric car, using a solar panel, right? You can use your car. So that's the one direction, charging from the solar panel, charging your car. At night, there is no solar radiation, right? You want to use the energy that is stored in your car's battery to use in your home for your appliances. So that means you need to have bidirectional power flow. And SST, or solid state transformer, provides that for you. A little bit about the architecture of this SST. It is usually based on 1, 2, or 3-stage configuration. Let's talk about the 3-stage configuration, right? 3-stage configuration is AC to DC, right? So it converts medium voltage AC that's coming from your grid to a medium voltage DC, okay? Here between these two, you have your DC link. The next stage is DC to DC. This stage provides your isolation as well, because you need that for protection purposes. You need to have that galvanic isolation. So it uses a high frequency transformer for galvanic isolation, and typically implemented with dual active bridge, single active bridge, or LLC resonant converter. This is just the type of the converters that we can use. The last stage is again DC to AC. So convert the low voltage DC back to the low voltage AC, right? So these are a few application. This is the 3-stage configuration for SST. What are the applications, you might ask? You can use for railway traction, for smart grids, as I just mentioned, because you want to integrate with your smart grid, integrate it with your renewable resources, your PV, your wind, EVs. You can use them for ultra fast chargers. I will discuss that, and data centers. Right? Some of them in the next few slides I will discuss. For second application, railway traction, they are based on SST. So traditional medium voltage AC system, they use your traditional low frequency transformers and rectifiers. This is, as I mentioned, this is bulky, this is less efficient. Now medium voltage DC systems now are gaining some ground because it is simpler. You need less reactive compensation, less loss in this case as well. So they have come and tried wide-bandgap devices for this. An example for you, they have used 10 kilovolt silicon carbide MOSFET that outperforms your traditional silicon-based IGBT. IGBT is a device. We are not going to discuss the details of what device is, but it's not different from MOSFET. So what they got 98.93% efficiency, demonstrated in 300 kilowatt megavolt DC converter, and they used 3.3 kilowatt silicon carbide. Another example, Japan's Tokyo Metro deployed hybrid silicon carbide SST, solid state transformers, and they achieved 70% weight reduction and very high efficiency of 98%. Economical barriers for this, generally speaking, wide bandgap devices, they are still expensive, right? For this reason, just very quickly, generally speaking, they are expensive. So one of the barriers for railway traction is their cost. Although it is decreasing rapidly, but it still is the problem. So to solve that issue, they are using hybrid as well, hybrid configuration. So they can use silicon and silicon carbide simultaneously to use the benefits of the both cost and the benefit that silicon carbide offers to reduce the cost at the same time. The next application is data centers. We understand data centers are expanding rapidly, and one of the reasons is AI. They need the data centers everywhere. They're becoming a major problem when it comes to the grid, and that's why they think in the future, electricity will become very expensive because it's like a black hole. It sucks all the energy, this data center. So it's very important to make data centers efficient in terms of the energy or the power they use. So that's where power electronics comes in. That's where the wide bandgap devices are coming in. What they do, they want to transition from AC to medium voltage DC to improve the efficiency. So wide bandgap devices, they enables server power supply units, but they are making improves the so wide bandgap based PSUs, server power supply units, are more efficient, compact. They can support higher power densities and obviously reduce the energy loss. So this allows for more servers per rack and lower total energy consumption. UPS, when it comes to uninterruptible power supplies, wide bandgap devices improve the efficiency and reliability of UPS systems. The idea here is to want to make sure you have a stable, very important, backup power, which produces less heat. Wide bandgap devices offer that. Solid state, when it comes to solid state transformers, we discussed that. We understand the benefit there, still used in data centers, and rack level power conversion. So what happens is wide bandgap devices enable direct high voltage AC to DC conversion, right? And that can happen at the rack level, directly behind the server. And this minimizes the distribution losses because that happens right at the rack, not somewhere else, and then bring it there. And that allows for more efficient power delivery to the server. Generally speaking, system level, if you'd have wide bandgap switches, you are reducing your cooling requirements, you have a smaller footprint, and you have a better reliability when it comes to data centers. So these are the benefits of wide bandgap. The next one, really quickly, I have two more to talk. Electric vehicle chargers. Okay? Now, with the increase in electric cars, issues still exist. Some of them, they exist, and challenges range anxiety, right? People, they don't buy electric cars. Some people, they don't buy electric cars because range anxiety. So to solve that, they need to have ultra-fast and efficient chargers. Okay, that brings us to onboard chargers. So what is onboard charger? So it's the electronic device. It's built into an electric vehicle that converts AC, alternating current, to DC, right? Because batteries they work with DC. So this is there for you to be able to connect basically your car to the grid and charge your car. Same way as your phone actually works, right? You're doing the same thing. Now, if they use wide-bandgap devices, they can improve the efficiency and also reduce the size. Same way your phone charger became smaller, right? Ultra-fast charging, you can replace low-frequency transformers with direct medium volt grid interface using SST, your solid-state transformer. GaN here is not very used because of, as I mentioned, GaN excels in high frequency, not high voltage. System level benefits, we discussed that in previous one. Generally speaking, it reduces the passive component size, lower cooling requirement, and improved overall economics when it comes system-wide. The last application I would like to cover here is solid-state circuit breakers. We know what circuit breaker is, right? Circuit breaker is a protective device that automatically interrupts the current flow when a fault comes in. That fault can be a short circuit, that can be a overload current, right? It's designed to protect equipment and can reset to restore power after the fault is cleared, right? Traditionally, circuit breakers are electromechanical, okay? They rely on magnetic mechanism to detect the fault and physically separate the contact. That's literally a contact that is separated, right? At very high, the contact separated, that's physical. At very high voltage, you can imagine if I physically separate a very high voltage at arcs, right? That's why circuit breakers, they have to distinguish this very, very, scary arc. That's why they're using SF6, they use it in vacuum, they use it in oil, okay? And because this is electromechanical, obviously, it's slower. Okay, we are talking about milliseconds, right? Is a slow, we mean milliseconds, right? But still, they are very, very slow. As we discussed, power systems become faster. They become more complex. Okay, they need protection equipment. They are equally fast. They are fast. They are high performance. That's where your solid-state circuit breakers come in. Okay, they are essential for fast protection in medium volt DC grids. Some examples here for you from literature. 650 volt GaN. It could interrupt a short circuit current at 282 nanoseconds. How faster they are. Compare that to milliseconds of ordinary or traditional circuit breaker. They use 1.2 kilovolt silicon carbide, showed 570 nanoseconds. At the 380 volt short circuit, which is massive. Another example showed 1.5 microsecond interruption for 75 amp short circuit, with a voltage of 1200. If you want to go at higher currents, you can usually parallel these things together to achieve higher current. future is wide bandgap solid state circuit breaker, because firstly it doesn't have any arcing. As I mentioned, it's the traditional circuit breakers they will have, because it's physical, right? It is literally a contact. And so when you separate at high voltage, imagine that 1200 volt, it will arc. But because we are talking about wide bandgap devices, there is no arcing, right? Because there is no physical contact. We are talking about sub-microsecond response and also low maintenance, which is very important. That brings me to the end of this seminar presentation. Thank you for your attention for this. I stop sharing my screen, Tony, if you like to take control.
Yes, you can. I think you can stop sharing.
I think I did.
Yes, I'm going to quickly share mine, then we'll be finishing. Just a moment. Yeah, we'll be finishing just now. But yeah, thank you very much, Dr. Hamid. I think that was very insightful. And I believe that all the attendees, I think, thought so also. And they took a lot of knowledge from what you shared. And I would like to also thank our attendees for taking their time and joining us for today's presentation. I think there's only a few questions that I've seen on the platform. Yes, on the chat box, there's only a few questions. I'm not sure if you're able to see them, Dr. Hamid, on your side. Well, I'll just read them out to you then, if that works.
Yeah.
Okay. But yes, today's course basically covers what the courses that covers today's topics. As you can see, it basically covers electrical engineering and electronical engineering. So we do have various programs, as you can see, from professional certificate to graduate certificate. So I will send you a link to check more of the programs that you can do in this particular topic. And these are our upcoming courses, ECT and EIT respectively, professional certificate to Bachelor of Science in Electrical Engineering. And at the right-hand side, those are the dates for those particular programs. You can go to our website for more information. Our course advisors will then advise regarding any information that you may have. So on the screen now, this is the QR code you can scan to claim your certificate of attendance. I will also share the link now on the chat session, on the chat platform. So yes, this is the Q&A session. So I'll just read we have, I think, 2 minutes left. So I'll just read a question that I saw on the chat box to Dr. Ahmed. Just a moment. I'll just leave the QR code on the screen so that you can scan. Let me just go to the question that I saw. So the question that I have here, Dr. Hamid, is what is power consumption comparison, be it BET, SST, and traditional transformer? I'm not sure if you can see that question. What is power consumption comparison, BET, SST, and traditional transformer?
So transformer is basically used to to change the voltage level by itself. So is this Henry? I can see. Is it about the dissipated, how much power is the efficiency, or power consumption? Because by itself, transformers, they are there to transform the voltage levels. Okay, by themselves, they are not there to consume any power. So basically, what it means, they are more, depending on your application, it will be, it varies. But the thing is that is important is SST is more efficient when in comparison with traditional transformer. Not only that, they are smaller. They are used in bidirectional power flows. So these are the benefit of SST as compared to the transformer.
Thank you very much, Dr. Ahmed. I think there's just one more question. I think we'll be then wrapping this. And as I've mentioned before, the presentation will be sent to your email, so just keep an eye on that. I saw a question. It reads, how many voltage does DC have maximum equals to? And AC have maximum equals to? I'm not sure if you can see the question.
Sorry, the question is not clear.
How many? I'm not sure. How many? This is the question. Let me just put it on the chat now. I think you'll see it. That was the question. I'm not sure if that is the full question. Do you see it, Dr.
Voltage does if that means what voltage levels are we talking about? We are talking about a few thousand volt voltage. If that's what they mean, this was the maximum DC voltage. Depending on application, there is no limit. In train, you can go tens of thousands volts and very high currents as well.
Okay.
The maximum can be tens of thousands volts. There is no set value for the maximum voltage as we demand. Obviously, we have to have devices for that to support, but we don't have the devices. That's in some for many applications, I believe.
Okay. Once more, I would like to just express my gratitude and thanks to Dr. Hamid for this wonderful presentation, an insightful one. And I just saw some chats that it was insightful, and they do appreciate. I think we are at the end of the presentation. On our screen, those are the details that you can contact us. Any last words from you, Dr. Hamid, before we wrap up?
Thank you very much, and thanks everybody for attending this session.
Okay. Thank you, everyone. You guys have a great day. We are ending the session now. Thank you.
Thanks, everybody.
Everyone.